today. We have two little tidbits to add to today's class in simple harmonic oscillators. So I'm just going to get right to it. If you look at the equation of motion for a simple harmonic oscillator, A cosine omega t plus delta. We know the amplitude is the amplitude of the oscillation, and what that means, if you consider, so I'm doing a little background to the little tidbit. The blue box here is the cosine of a number, and if you only graph that, you're going to get something that looks like the cosine function. And the largest and smallest value you can get of that is 1 and -1, because it's the cosine function. However, if you now multiply A, the amplitude, times this varying number that varies between -1 and 1, if I now multiply A, the amplitude, which is the greatest distance this oscillator ever is from equilibrium, you now are going to have a function that varies between -A and A. And so that's the amplitude of the oscillation, that's the amplitude of the function. Okay, nothing groundbreaking there. If I now differentiate this with respect to time, I get velocity as a function of time, and I get -omega A times sine of omega t plus delta. Well, similarly, for this function, I have this part of it, which is a value that oscillates between -1 and 1, and I then have this in I'm going to choose a different color, inside the red box. That is what I multiply this varying value between -1 and 1. I multiply by this to get the velocity. This is called the velocity amplitude, because if I look at the value of omega times A, and let's say for the sake of argument that the value of omega times A is 6, okay, if it equals 6, well, it won't just be 6, it's going to have units. Let's see, the units for radians per second, for omega are radians per second, and the units for amplitude are meters. And so if you multiply those out, you're going to get 6, oh, look at this, 6 meters per second, because the radians, of course, is a meter per meter. That is a dimensionless quantity. And I end up with just meter per second. This is the velocity amplitude, and that is the largest value you can have for the velocity of this oscillator. And it's also the amplitude of the velocity function. Likewise, if you differentiate this guy with respect to time and get the acceleration as a function of time, you, of course, get -omega squared A times cosine, all that stuff. And this inside the green box is the acceleration amplitude, or its value is the largest or the maximum acceleration you can ever get for this oscillating thing. So if they ask you for the maximum velocity or the maximum acceleration, that's where you find them, the coefficients of the trig part of the velocity and acceleration functions. That's tidbit number 1. Tidbit number two is simply this. We derived today that, for instance, the period of a simple harmonic oscillator is 2 pi square root of k over, I just got that backwards, m over k, thank you very much. If you remind me in a second, I'll tell you how I remember that, because it's easy to get mixed up, m over k, k over m, and there's an easy way to remember how to get it right every time. But you'll have to remind me to do that for you. Okay, this k we said today in class is SHO, the proportionality constant between the amount of displacement of an oscillator and the restoring force on it. If your oscillator happens to be, because we emphasized today that's not spring constant. Well, it can be spring constant if your oscillator is set up so that the only force, the restoring force, is a spring force. So if you have a block on a frictionless surface with a horizontal spring, like so, and it's oscillating back and forth. So this would have to be a spring that can both compress and stretch from its unstretched position. Then the only force on this oscillator is the spring force. And so the restoring force is simply a spring force. And so SHO is the spring constant of that spring. So SHO isn't always spring constant, but it might be, and it is in this case if you have a block oscillating because of a horizontally mounted spring on a frictionless surface. That's going to come with a couple of problems. Oh, the problems, you say. What are the problems? You want numbers? I got numbers for you. Here they come. They are Chapter 14. Numbers 29, 31, 32, 36, 47, 59, and 62. It looks like a lot because it is, but these are not so conceptually demanding as just basically getting through the nuts and bolts of this stuff at this stage in the game. So have fun, get them all right, and I will see you tomorrow. Thank you very much.